So this is section 4.4. I have a video on 4.4 already. This is kind of a refresh of that video. I had an error in one of the examples there, so I had to fix that. I removed some examples. I've added some different things. So if you've already watched that, some of this will be familiar, but not all of it. So we've got 6 trig functions, and we're introduced to them in terms of a right triangle. And I always use right triangle whenever I do my trig. So we've got sine, which is opposite over hypotenuse, cosine, which is adjacent over hypotenuse, and tangent, which is opposite over adjacent. Those are the big 3. And then the others are the reciprocals of them. And to remember the big 3, I just think of SOHCAHTOA. So sine O over H, and then ca is cosine adjacent over hypotenuse, and then the TOA part is tangent opposite over adjacent. Otherwise, you have notes, so you can, if you choose not to memorize it, which is totally fine, you can, just at least have it written down somewhere so that you know what you're trying to find. Everything we do with trigonometry is generally based off of the unit circle. So this comes from the equation of a circle centered at the origin with radius 1. So it's called the unit circle because 1 is a unit. That's sort of where it comes from, is the radius being 1. And so the equation of a circle is x squared plus y squared equals 1. So if you're going into calculus, this is going to be important because you will, I think it's in Calc 2, start talking about other different types of coordinates, and you start talking about polar coordinates, which is based off of trigonometry. You have the radius and the angle. And so you're converting your x and y into a radius and an angle. So you're using trig to convert from one set of coordinates to the other. So when we're on the unit circle, we have our angles always starting on the x-axis, the positive x-axis, and then we go counterclockwise. And so you can always sort of form a triangle as you're going around the unit circle, and you can spin around and, go around the unit circle as many times as you need. So I will always kind of draw triangles here. So this would be, you just kind of finish your triangle, and then that gives you a right angle here that you can use to do your trig. Now these images come from the book, and it has this thing labeled T. That is the arc length that is labeled as T. So the arc length is basically the distance along the circumference of the circle. It's not the same as the angle. And so they've just taken this curved distance and then translated it to a vertical distance just to kind of demonstrate that. But that's what T is standing for. T is the arc length, or the length along the circumference of the circle. So when we take those 6 trig functions and then we look at them in regards to a circle, and it doesn't have to be a unit circle, it could be any radius. Instead of doing opposite over adjacent, we can use our coordinates x, y, and then r for the radius. And that's what we're going to be using today, is we're going to be using our trig functions in the form of x, y, and r. And you use the Pythagorean theorem to basically find the r if you don't know it, because you've got this right triangle that you draw, and then you use the Pythagorean theorem to get there. So these are derived from the Pythagorean theorem. It comes from basically the circle formula, because that's related to the Pythagorean theorem with the x squared plus y squared. And the distance formula, actually, if you look at it, you're basically finding the distance from x, y to the origin 0. So it is also using the distance formula. So all of these are kind of related because they're all kind of based off of the same idea. So, excuse me, we're going to be referring back to this slide a lot because we're going to be looking at things in terms of x, y, and r. And so this is something, you're going to want to have definitely for your discussion where you're making a cheat sheet, you want to have the SOHCAHTOA stuff. You want to have the unit circle stuff. You want to have them in terms of x, y, and r, because that's how we're going to be using it. So We're also going to be using knowledge about the signs of various trig functions. So the top image here is kind of giving you what happens with your x and your y, whether it's positive and negative, and then where the angle is located. But it's a little bit easier to look at this information in terms of the signs of the big three. So these are basically telling the same thing. It's just with the top image, you would have to use your formula like y over x to figure out that what sign the tangent is. The bottom image is kind of doing that for you. So we're definitely going to be using knowledge of the signs of the big three in various quadrants. So this is going to be something else that you're going to need to know, that like quadrant 1, everything's positive. Quadrant 2, only sign is positive, and so on. So we're going to be referencing this because we need this when we're trying to figure out the values of the trig functions. Reference angles. So this is another thing that comes up that you have to talk about in your discussion. And we're going to do a little bit with reference angles just to kind of introduce you to the idea. Is reference angles are actually going to be used more in when we start solving trig and go a little bit beyond this section. This is sort of like an introduction to reference angles. The majority of what we're going to be looking at is not necessarily utilizing the idea of reference angles, though we will a little bit. So the reference angle is always in regards to the horizontal axis. So when you're in quadrant 1, your angle is the reference angle. It's the same thing. But when you're in the other 3 quadrants, your reference angle is different because we're always comparing it to the horizontal. It's basically the angle that you would form when you create your right triangle. So like if I made this, oops, thought I was on the pen. So in quadrant 2, when you create your right triangle, the reference angle is the angle in that right triangle that you'd be using for your, your SOHCAHTOA stuff. Same thing with quadrant 3. So these are all based off of the actual triangles you would draw in order to get to the horizontal and do your SOHCAHTOA. So that's what the reference angle is, the actual angle you're using for SOHCAHTOA. Now, determining the reference angles is a little tricky because you can't just say, oh, I'm always subtracting 180 or 2 pi. It depends on which quadrant you're in. And so it's going to be important to kind of write these down so you know which direction, because if you notice in quadrant 2, you're taking 180 minus your angle, but in quadrant 3, it's the other way around, your angle minus 180. And then when you're in quadrant 4, it's 2 pi minus your angle. So you have to kind of know where you're at to figure out what your reference angle is. So we're going to start out by just practicing this reference angle so you have an idea, but we're not going to use it too heavily for the rest of what we're doing. This is just kind of to get you a little bit introduced. You'll need it kind of a little bit further on. So the reference angle, we always reference with theta, and then it's basically theta prime. When you have that, it's an apostrophe there, we read that out loud as prime. So that is read out loud as theta prime. So we want to find the reference angle first for 309 degrees. So I always draw my unit circle. And I don't even really need to draw my unit circle. What I really care about are my core, where I'm at on the unit circle. So we start at 0 degrees, then we're at 90 degrees, and then we're at 180, and then 270. So you can look on the unit circle and get those same angles. I don't really need to draw my circle here. I just need to know what the core angles are if I was dividing up the 360 of a circle. So 309, so 0 is the same as 360 degrees. So we know that the 309 is somewhere in quadrant 4. And I don't care if I'm to scale or not. It doesn't matter. I just know that I'm somewhere here. So this 309 degrees is we're always going counterclockwise, and we start in quadrant 1. So 309 degrees is going all the way around through most of the quadrants there. And then we kind of get partially through the 4th quadrant. the reference angle we're looking for is this right here, theta prime. So when you are in quadrant 4, you can find the reference angle. Let me go back to my slide where I had that. So we're in quadrant 4, you find the reference angle by taking 2 pi, or we're in degrees right now, so we're going to do 360 minus your angle that you have. And this makes sense because we know that the whole circle is 360 degrees. We have 309 degrees, so the remaining angle must be whatever we need to get to 360. So our reference angle, theta prime, is just 360 degrees minus 309 degrees. And when you're doing this, you want to make sure that you do use the degree symbol, because if you don't use the degree symbol, then it's assumed to be radians. So whenever you're doing your math and you're using degrees, you have to have that symbol because that tells you you're in degrees, not radians. So our final answer here is 51 degrees when you do that. So our reference angle, the angle that we would use if we were using a right triangle here, is 51 degrees. So let's look at the one on the right. We've got theta equals 4.8. So there's no degree symbol, so we assume that this is radians. So you really have to, pay attention to what is their degree symbol or not, because if you're given a number and it doesn't have the degree symbol, it is radians. So radians are always in terms of pi. So I'm going to have we're going to start with 0. And then when we're doing radians, this is pi over 2, pi, and then 3 pi over 2. So 4.8. So pi is 3.14. So we know that 4.8 is bigger than pi. But we want to know, is it less than 3 pi over 2? Kind of where is it located? So there's 2 ways you can do this. You can do 3 pi over 2 on your calculator and kind of see what that is as a decimal. Or you can take your number that you have, 4.8, and divide it by pi to find out how many times pi it is. And I actually recommend you do that method, because sometimes you might have an angle that's larger than 2 pi and you need to figure out how many loops of the circle you're going around. And so just relying off of the numbers that you have here wouldn't kind of tell you how many loops you have around. So I recommend what you do is you take your 4.8 and divide it by pi. And this is just going to give us an approximation. And it's about 1.53. So this is telling us that 4.8 is, I should use the about, not equal, is about 1.53 pi. So 3 pi over 2 is 1.5 pi. So we actually, this tells us that we're going to be somewhere over here. So this is actually very similar to what we did with the 309 degrees, but now we're in radians. So instead of doing 360 minus, we're doing 2 pi because that's the radian value of 360. So we're looking for the reference angle, which is this angle right here, theta prime. So we're going to have 2 pi minus 4.8. So you could do 2 pi minus 1.3 pi, which is actually, might even be easier, 1.53 pi. And so this tells us that it's 0.47 pi. And that's a completely valid answer for your reference angle. The other thing you can do is just approximate that as a decimal. So 0.47 times pi. And you can say, okay, it's about 1.47 0.48 and radians. So 0.47 pi is also radians. It's the same thing. You can just choose whether you want to write it in terms of pi or you want to multiply your number by pi to get an actual numerical value. But either way, that is what our reference angle is. I personally find doing it in terms of pi a little bit better because then I'm like, oh, okay, it's less than pi over 2. So I know that, it kind of gives me more of a visual based off of our quadrant, because when we use the unit circle, we always do everything in terms of pi. So that's why I like to figure out how many pi's it is. It just helps me understand where it is in regards to the unit circle versus 1.48. It's just a little harder for me to kind of think of that in terms of where are we in our unit circle. So is there any reason someone would use radians instead of degrees? Yes. Basically, whenever you do calculus, it's always in radians. So most of mathematics is radians. We default to everything in radians. A lot of the math is easier when it's in radians. So you want to get familiar with doing things in radians. You want to get more familiar with radians than degrees, because pretty much any math going from here is done in radians. It's very rare to see degrees. The only time you might see degrees if it's linked to an actual real world application, but any of the engineering stuff you do is always going to be radians. So I always just keep my calculator on radians mode. And then if I'm given degrees, I convert it to radians because that's just what I'm familiar with.
How do you convert it to radians?
So that is, we have a conversion, two conversions. So we know that 360 degrees is equal to 2 pi, or 180 degrees is equal to pi. So I use the 180 and pi. And so what you do is dimensional analysis to do your unit conversions. This is the same thing that I mentioned in my announcement yesterday. So in the homework problem number 1, you have to do a unit conversion. You need to do that with dimensional analysis. That is the correct way to do unit conversions. So if we wanted to know, say, the 51 degrees, what that is in radians, you would say you have 51 degrees, and then you multiply by pi over 180, because you basically want your units of degrees to cancel. So you need to have those diagonal. And so then you just do that math, which is really, we're going to do 51 divided by like 180. Generally, we'll kind of leave it as a fraction. That I don't think is even reducible. 51 is prime. So you would just have 51 over 180 pi, or if you did want to approximate it, you would put like 2.28 pi, because usually the radians, we want to kind of keep it in terms of pi, or you can, actually multiply it then by pi, which comes out to 0.89. So you'd have 0.28 pi radians or 0.89 radians. Those are equivalent. Or you would have 51 over 180 pi radians. But to convert it is you multiply it by pi over 180. And then to do it the other way around, if you have radians, then you do 180 over pi. Your goal is to get your units to cancel out diagonally. And that's what dimensional analysis is that you're making sure that your units are canceling. And we don't need to write like rad, like I did on the right. That's not a requirement, because you're assuming that if there are no units on your angle, that it is in radians.
So the reverse process, you just multiply it by 180, really?
Yeah, you would have, but you have to do 180 divided by pi. So if I wanted to, let's take our, we have 4.8. If I wanted to convert that to degrees, that's in radians. So I need to have pi in the denominator and 180 degrees in the numerator. So it's 4.8 times 180 divided by pi. And so that comes out to 275.02 degrees roughly. So you have to make sure that your units match and you're just multiplying and dividing to do those unit conversions. Are there other questions? Okay, got a couple more reference angle here, and then we'll get into more right triangle stuff. So we've got an angle of negative 215 degrees. So I'm going to start with kind of labeling it again. I'm going to just label my degrees so I have an idea of where these are located. So conventionally, we go counterclockwise. If we go clockwise, that is with a negative angle. So the negative says you're going the other way around. So 270 degrees is equivalent to a negative 90. 180 is actually the same as negative 180. And then 90 is a negative 270, where you're going in the other direction. So negative 215 is going to be somewhere in quadrant 2. So that is negative 215 degrees. So our reference angle is going to be this angle right here between basically, I guess if I do it in terms of like, you've got that negative 180 and then your negative 215 degrees. So you can think of it in terms of your negatives, or we've got this 180 angle and then we've got negative 215 degrees. And so we want to find what our reference angle is. So let's go to our little chart with the reference angles. So we're in quadrant 2. And so when you're in quadrant 2, it is 180 minus your angle if you're in degrees. So currently we've got a negative angle. So if we do 180 minus a negative 215, that's going to be basically adding. And then that gives us an angle that's outside of 360. That's not actually what you need to do here. We've got 2 steps here, because we have to first convert our negative angle to the positive version of the angle. So we need to actually first find what is called the coterminal angle, the angle in red. And so to do that, you're just doing 360 minus 215, and that will get you the coterminal angle. Because in order to kind of figure out these reference angles, you need to have them in the positive version. So this is 360 degrees minus 215 degrees, which gives us 145. Oops, not 140, 145 degrees. So now that we have the actual coterminal angle, now we can do 180 minus that angle. We're going to do 180 minus 145 to get our reference angle. So you have 180 degrees minus 145 degrees. And that comes out to 35 degrees. So your reference angle is 35 degrees. So you have a couple steps here when you've got this negative value, because you have to get it into the positive, going the correct direction when we do our angles, and then you go from there. The other way to think about it is if you've got this 215 degrees, you can subtract out the 180 and that will give you 35, but you have to then ignore the sign. So it's you have to kind of like think about, well, what am I finding? And with the negatives, it kind of gets a little confusing, but this is the proper way to do it, is to first find the coterminal angle and then the reference angle based off of that. So next one here is 7 pi over 6. So this is in radians. And just because it has pi doesn't necessarily mean it's radians, because you could give angles that are in degrees with pi in there. The key is that it doesn't have the degree symbol. And that's how you know it's in radians. So we've got 0, we've got pi over 2, we've got pi, and 3 pi over 2. So we have 7 pi over 6. So I like to change all my denominators to be with a denominator of 6. So I can really see where is the 7 pi over 6 going. So I can really compare it, because if you're comparing something with a denominator 2 to something of denominator 6, it's a little bit harder to kind of figure out where your locations are. So pi over 2 is the same as 3 pi over 6. Just multiply the top and the bottom by 3. Pi is 6 pi over 6. And then this would be 9 pi over 6. So when I convert them so they all have a common denominator with our angle here, which is 7 pi over 6, then we can see where we're actually located. So we are going to be kind of over here with our 7 pi over 6. We're a little bit beyond 6 pi over 6, but not yet to 9 pi over 6. So we're in quadrant 3. So when you're in quadrant 3, you take your angle and then you subtract pi, or 180 degrees. So we're in radians, so we're going to subtract pi from our angle to get the reference angle. So our reference angle here is basically the difference between 7 pi over 6 and 6 pi over 6. So this one's pretty easy to do. You can kind of think about it. So, but you just subtract, and then we just get pi over 6 as our reference angle. 7 minus 6 is 1. So the reference angle is pi over 6. Are there any questions? Okay. So now we're going to move on to kind of like the bulk of what we're going to be doing, is kind of figuring out the answers to sine, cosine, tangent, and stuff like that. We are going to kind of just start with this table of common values. So we've got 0, 30 degrees, 45 degrees, 60 degrees, and then 90, 180, and 270. There are, divisions between 90, 180, and 270 that, you've got 3 pi over 4, 5 pi over, all of those things, but these are just the most common that you're kind of working with. And then they're the radian equivalent. And then sine, cosine, and tangent. So to get the other 3 trig functions, you just take reciprocals here. So this is just good for reference. You can have it in table form, or you can find a unit circle that has the common trig values, whatever you is easy for you. So we're going to start by just kind of using this table so you can just kind of see how it can be used and just get familiar with the idea of the unit circle and the signs of the trig functions, because we're going to be taking into account the quadrants and that sort of stuff. So we're going to just start with this example here where we want to find 2 solutions of each equation. So the first one is we want 2 solutions to sine theta equals 1/2. So we're looking for 2 angles where the sine is equal to 1/2. So you start by going to your common angles. You know, you go to your table here and you're like, well, where is my sine equal to 1/2? So there's only one spot on this table where it's equal to 1/2, and that is 30 degrees or pi over 6. So we're going to use pi over 6 because, you know, we want to get used to using radians. That's going to, you know, what you're going to be using most of the time. So one of the solutions is an angle of pi over 6. So, you know, one of them is pi over 6. But how do you get the other solution? So this is what I do. I first kind of draw where is my pi over 6 in terms of, you know, on my unit circle or on my grid here. So I've got 0, pi over 2, pi, 3 pi over 2. So pi over 6 is right here. So that is the angle of pi over 6. And that gives us a sine of 1/2. So we want to know where else will we get a sine that is 1/2, or basically we'll have the same sign. So we're going to go back to our chart here with the signs in the trig functions. So I'm looking at the bottom here. In quadrant 1, our sine was theta is positive. So we want to say where else is our sine of theta positive, because it's basically going to have the same number. So that is in quadrant 2. So quadrant 2 also has the sine of theta being positive. So that what this tells me is that I'm going to have a second solution, and it's basically going to be a mirror image. So the second solution is going to be this angle right here. So we're taking that idea of reference angles, because the reference angle here is essentially pi over 6. And we want to find what is the other angle that goes with it. So you just do pi minus pi over 6 to get the second solution, because it's going to have the same sign and it's going to be the same value, because the value is the same, because it's essentially the same exact triangle that you would form. It's just kind of mirror image. So our second answer is pi minus pi over 6. So pi is 6 pi over 6 minus 1. That's going to be 5 pi over 6. So we have two answers here. 5 pi over 6 and pi over 6. So we had to kind of use that reference. We're using that chart of common values. We're using the reference angles, and we're using the fact that of different quadrants and their signs to kind of figure out what the second solution would be. And there's more than two solutions, because the thing about the unit circle and just trig is that you can go around the circle infinite times. But we generally want all of the solutions that are between 0 and 360. And so there's only two of them in that, you know, the main unit circle, two solutions. So let's look at the second one. We have cosine of theta equals square root of 2 over 2. So same thing, we're going to just use our chart and say, where do we have the square root of 2 over 2 for cosine? And so that comes to 45 degrees, or pi over 4. So we know one of our solutions is pi over 4 based off of our chart here. So I'm going to just write that down. And then I'm going to kind of look at where we're going to be on our grid. So pi over 4 is halfway between 0 and pi over 2. So one of our answers, pi over 4 right there. So this was a positive cosine. We want to know where else is our cosine positive. So we go to our chart of quadrants and then we look where else is cosine positive. And in this case, it's quadrant 4. So quadrant 4 also has a positive cosine. So that's going to be where our second solution is. So this is again going to be a mirror image, but it's basically in the other direction. So we want this angle right here. And our reference angle is pi over 4. This is actually kind of nice because it's this just like before with our sine, we have our reference angle based off of our first solution. So our reference angle here is pi over 4. So now we go to, well, how do we figure out, what do you do with your reference angles to find your other angle? And we're going to do 360 minus that reference angle. So if I go back to, it's basically, oops, wrong one. There, I wanted this one. So to find the reference angle, you do 360 minus your angle. If you're given the reference angle, you do the same 360 minus your reference angle gives you the other angle. So they kind of work very similarly. So all we need to do to find our other answer here is 360, or in this case, 2 pi minus pi over 4. And that will give us our other answer here. So common denominator here, 2 pi is going to multiply by 4, 8 pi over 4. So 8 minus 1 is 7 pi over 4. So that is our second solution to this equation. So the two answers where our cosine is square root of 2 over 2 are basically both positive, is pi over 4 and 7 pi over 4. Any questions? Okay. So now we're going to start finding our 6 trig functions. We're going to be, in this case, we don't actually really need to know the reference angle stuff. Now we're going to be focusing on the fact that like sine, cosine, and tangent or SOHCAHTOA are basically where they are in terms of x, y, and r, your radius. We'll be using our quadrants and the signs of the quadrants to kind of help us decide what our values are here. We're going to be using the Pythagorean theorem. So we want to find the exact value of the 6 trig functions of the angle shown. So we're given an angle and we're given an ordered pair that if you were to draw that line would be have that angle in regards to our horizontal, kind of our starting point here. So we're not given an angle in this case. We're not looking for an angle. We're looking for the trig functions based off of this. And so this is where you want to create a triangle that has that reference angle, but we don't care what the actual angle is. We don't need to know the angle in order to solve this. We just have to draw the triangle that creates the reference angle. So step 1, got all my papers here. I've got all my step 1. I like to have this is you want to draw your right triangle. And so it doesn't have to be to scale. And we've got our x here is -12. So I'm going to use -12 on my right triangle. Even though the length of a triangle can't be negative, it doesn't matter here. I'm going to use the negative because that's going to help me when I'm doing the SOHCAHTOA stuff to find my trig functions. So our x value is the horizontal, that's -12. Our y value here is -5. So that's going to be, we're going to use that as our vertical here. And in order to find the 6 trig functions, you need to have all parts of your triangle. So we need to find what the radius here is, or what our hypotenuse hypotenuse is. So you need to use the Pythagorean theorem. And for the Pythagorean theorem, your radius is always going to be positive. So you don't have to worry about positive or negative, whatever. You're always going to use the positive value when you're solving for the radius or the hypotenuse part. So this is a -5 squared plus -12 squared equals our radius squared. So it's a squared plus b squared equals c squared, or x squared plus y squared equals r squared. Basically that equation for the circle. So that's 25 plus 144, which gives you r squared, which is 169. And the square root of 169 is 13. So I'm going to label that on our triangle here. So in geometry, you might have learned about special right triangles. This is a 5, 12, 13 triangle, but we've got negatives here, and that will help us get the correct signs on our trig functions. So once you've completed your triangle, you drew your triangle, you did your Pythagorean theorem, now you can use your triangle to find the 6 trig functions. So that's basically step 3. And so what I do at this point is you can do 2 things. You can use these right here and think of the idea of opposite over hypotenuse, and then think about like where your angle is. You're using the reference angle when you're doing it this way. But I find it easier at this point because we've got like an ordered pair, we've got X's and Y's, is I use this version right here. Because I know what my X value is, I know what my Y value is, we just found R. So these are the values that I use to find my 6 trig functions. I use Y over R, X over R, Y over X, and then I find the reciprocals. So I actually have these written down because I don't have them memorized. So I have them written down on another sheet of paper so that I can just kind of copy them down here. But this is what I do. So our sine of theta is Y over R. And so our Y value here is -5. And our radius is 13. So that means the sine of this angle is -5 over 13.
He goes by John.
Cosine is X over R. So that's coming from that slide that I showed you. So our X value here is -12. So it's going to be -12 over 13. And then tangent of theta is Y over X. So our Y value is -5. X is -12. So this is going to be 5 over 12 since the negatives cancel. So I find the big 3 using what the that slide has with your X over R stuff. So I don't have to, kind of figure out, because if your angle, essentially the reference angle is what we're looking at here, and you can do SOHCAHTOA from there with your reference angle and think opposite over adjacent, all of that. Or you can just say, okay, I've got my X, my R, my Y, just plug them in. Then to find the other 3, it's just the reciprocals. So the reciprocal of sine is cosecant. So that is going to be a -13 over 5. The reciprocal of cosine is secant. So that's going to be a -13 over 12. And then the reciprocal of tangent is cotangent. So that's going to be 12 over 5. So I find the big 3, and then I find the reciprocals to get the other 3. Now we've just found the exact value of these 6 trig functions just based off of a single ordered pair. We don't need to know what the angle is to find the values of the trig functions here. Are there questions? Okay. So here we didn't really have to use the fact that we have, the sine of quadrant and to because our missing value is always positive. But sometimes you're trying to find something like this and your missing value is maybe your X or your Y, and you need to know, is it going to be a positive or a negative? You kind of need to know what quadrant it is so you can determine what's the sign of the number is going to be. So here's kind of it's we're doing the same idea, but we're given different information, you know, and there we're given an ordered pair. Here we're given one of the 6 trig functions, and we're given a piece of information to help us determine what quadrant we're in. Because remember, we saw that a cosine, if it's positive, there are 2 different possible answers for the angle, or basically 2 different quadrants where you get cosine is positive. So if all we're told is that the cosine is 8/17, there are 2 potential places where that could be. So we need a second piece of information to actually tell us what quadrant that's in, and that's the tangent theta being less than 0. So that will help us narrow down between the 2 possible locations on the unit circle where we are actually located. So we have cosine 8/17. So I'm going over to our quadrant stuff here. Cosine is positive, so that tells us that we are either in quadrant 1 or quadrant 4 from that piece of information, the fact that we know the cosine is positive. So I'm just going to write that down here. So this piece of information, we're in quadrant 1 or quadrant 4. So next is tangent being less than 0. That means tangent is negative. So we need to figure out, well, where is our tangent negative? So I'm going to go to the same piece of information here, same chart, and then look, where is my tangent negative? So that is in quadrant 2 or in quadrant 4. So I'm going to write that down. So this is quadrant 2 or quadrant 4. So since both of these have to be true, this tells us that we must be located in quadrant 4, because that's the only place where both of these things are true. So that will allow me to kind of draw my unit circle. Now that I know what quadrant that I'm in, I can kind of draw my angle and get an idea of where we're at. So we're looking at something in quadrant 4. And this is our angle theta. And so this gives me an idea of my right triangle, because now that I know what quadrant I'm in, now I can draw my right triangle and fill in the correct information. So this is what my right triangle is going to look like. And we need to figure out, well, what is my X, what is my Y, and what is my hypotenuse here, basically. And we're not actually given an ordered pair here, but we know that the cosine of theta is 8/17. And if I go back to here, cosine is x/r. So we're going to have x/r equals 8/17. And so from that, we know that X has to be 8. So I'm going to label that, and that has to be a positive because of where we're located. We have a positive X there. And then we have R being 17. And so we need to finish the right triangle. We need to use the Pythagorean theorem to figure out what Y is. So I have 8 squared plus y squared equals 17 squared. And y here needs to be negative. I'm going to write that because we are in quadrant 4. In quadrant 4, your y values are negative. So I'm just putting a little note there that we need to, whatever number we solve with our Pythagorean theorem has to be the negative number. And this is usually where people kind of mess up, is they just take the positive and then they don't really think about, well, what quadrant am I in? So we get 64 plus y squared equals, I do not know, 17 squared. 289. That is a 1 square that I do not have memorized. Then subtract 64. So we get y squared equals 225, which tells us y is 15. But we want a negative 15. So remember, when you take square roots, you get a positive or negative value. And so we want a negative 15, because to be in quadrant 4, you need to have your y to be negative. So now I've got our triangle finished. We had to use the information of what quadrant we were in so we could determine our values and whether they're positive or negative. And now we can actually find the 6 trig functions. We already know one of them, cosine's already done. So that's good, you know. That's one less that we have to find. It's given. We just need to find the other 5. So sine of theta is y over r. So y is negative 15 and r is 17. So that's going to be negative 15 over 17. Then the reciprocal is cosecant. So that's going to be negative 17 over 15. It's the reciprocal. We already know cosine, that was given to us. So cosine theta is 8 over 17. The reciprocal is secant. So that's going to be 17 over 8. Then we've got tangent theta, and that is y over x. So that's going to be negative 15 over 8. Maybe I can squeeze that in. There we go. Kind of squeeze that. And so then cotangent is going to be the reciprocal, or negative 8 over 15. And so now we have found the 6 trig functions. And all we needed 2 pieces of information. We needed to know, you know, we got the location of one of our angles. And then we needed to know, like, or, you know, kind of the cosine, one of the trig functions of one of them, which gave us 2 potential locations. We needed to narrow it down with another piece of information. And then from there, you create your right triangle, and then you use the formulas in order to find the values of all the other trig functions. And you don't even need to find what the actual angle is to do this, which is nice. Are there any questions? Okay, so that is all we have time to go through. I could give you tons of problems, and I do have several others like on this presentation that we don't have time to go through. So what I will do is I will write the answers to them on the PowerPoint, and then you can try to figure it out on your own and see if you get the correct values. So that would be a good way to kind of practice, you know, whether you're understanding the what's going on here in order to do this. But this is, you know, being able to figure out what quadrant answers are in so you can get the trig functions. That's actually really important when we're solving for trig functions, because you need to know, because there's multiple angles that get you the same value of a trig function. So you need to know what quadrants it's in so you have the correct angle value. You know, we need to know the reference angle to make sure you're having the correct value as well, or coterminal. We like to give all of our answers between 0 and 2 pi. When we, you know, when you're going on to calculus or engineering, all this stuff, you're going to be given a lot of angles and trying to find other trig values. So this is going to be really important. So if you are going on to calculus, just you know, or engineering, if you're in engineering for sure, just keep all of this, all of these notes from this week, because you will need it.